Alright, hello class. So in this video we're going to look at the integral test and resulting p-series. That may sound familiar. Actually, it was a while ago when we were talking about improper integrals, but I believe I called them the p-integrals. But essentially what the integral test is basically is what I talked about in one of the previous videos, is that if you have a function f of x and the integral from, say, 1 to infinity of f of x dx converges, then that means that the series k equals 1 to infinity of f of k also converges. And I have a little picture here showing that, okay, if the full area beneath the curve shrinks to 0 fast enough for the improper integral to converge, then the rectangles with base 1, and that's what all of these rectangles end up being, is basically just a delta x equals 1. Because that would be f of 1, this would be f of 2, this would be f of 3, etc. Okay, then if the area, the actual area beneath the curve shrinks down to 0, okay, then the sum of the area of all these rectangles will also shrink down to 0 fast enough for the series to converge. So if the integral converges, the series also converges. Okay, so that actually gives us a really powerful way to analyze series that aren't necessarily a nice telescoping series. Okay, if we can integrate the sum end. And just when you hear me say that sum end, that's the thing being summed. That's this thing here. Okay, so if you hear me say that, that's what I'm talking about. Okay, there's a couple of things we need our function to satisfy, and we'll talk about that in the next slide here. But that's the gist, basically. If the improper integral converges, then so does the series, just like that. All right, so here's what the actual integral test says. And like I said, there's some conditions that you need for this to work. But they're maybe not as strong as you might think. So let's suppose f is continuous, positive, and decreasing for x greater than or equal to 1. And it doesn't have to be 1. It could be past a certain point. Okay, it could be any sort of maybe positive integer. Okay. Then the series k going from 1 to infinity of f of k and the integral from 1 to infinity of f of x dx either both converge or they both diverge. So that's really strong. Okay, we have a really good test here. The only problem with it is that, well, we have to be able to integrate f of x. And sometimes, as we've learned in this class, that can be a real pain in the butt. Okay, so it is a powerful test, but not always the easiest test in the world to use. Okay, and then this part, we do need to, at least in the back of our mind, keep this in mind, that it's got to be continuous, positive, and decreasing. So that means as the function approaches 0, it can't do things like this for its whole life, right? It's got to eventually level out. Now, if it acts a little weird here, but past a certain point, it behaves the way we need it to, that's fine, okay? We don't care what happens early on in its life, because even with the improper integrals, this part is just a finite area. We can just mark that as A, and then we would do the improper integral for that piece anyway. All right, so let's just look at some examples here, and then we'll talk about what the p-series are and how we get that automatically from the stuff we've already done. Okay, so let's look at this series A, which is the series k going from 1 to infinity of k over k squared plus 1. What I do want to mention is that this is one that we'll have a method for dealing with in a much easier way later on. Okay, but for right now, this isn't a telescoping series. It's not something that we could get a nice pattern out from our partial sums. So what we're going to do is try the integral test. Okay, now what we do need to check on is whether this is positive, and it should be positive because all our k's are going to be positive, so that shouldn't be a problem. The real problem would be decreasing. Okay, and a quick way to tell if something's decreasing is you can often take the derivative. So if you just say you're looking at x over x squared plus 1, this should be decreasing because this guy goes to infinity, but this goes to infinity much faster. I don't know why I put must. Much faster. Okay. And because of that, the denominator will be, you know, going to infinity faster and faster and faster, which is going to pull this function down to 0. Okay, so we shouldn't have to worry about it, you know, not decreasing over its entire life. However, if you still aren't convinced, you can always take the derivative. Okay, so the derivative, we'd have to use the quotient rule here. Right, so it would be the derivative of the top times the bottom left alone. Okay, minus the top left alone times the derivative of the bottom, which will be 2x. Okay, all over the denominator squared. Okay, we'll clean this up a little bit. We have an x squared plus 1. This will become a 2x squared. So the top will be a 1 minus x squared. And the bottom will have we'll just keep that the same. Now, for x greater than or equal to 1, well, at 1 we get a 0 on the top. So the bottom's always going to be positive. Okay, the bottom is always positive. But the top past 1, so the second we put 2 in here, we get a negative. So this whole thing is actually negative for x greater than or equal to 1, implying that f is decreasing for x greater than or equal to 1. Okay, so that is one way that you can check if you're not sure. If you can't just kind of eyeball it and see, oh, it has to be decreasing, or if you don't have a calculator, graphing calculator handy to take a look at the graph, you can always just take the derivative. Now, sometimes it will be difficult to kind of see what the derivative is doing, but in some, you know, most cases, oh, I probably shouldn't say most cases, in a lot of cases, it should work out fine. Okay, so this does satisfy the conditions. All right, so we can use the integral test. So the integral test, we're going to look at the definite integral from 1 to infinity of x over x squared plus 1. All right, and this is a U substitution. I'm going to use a quick U substitution because it's the denominator that I would make U. Okay, so it's a 1 over U case. So we're going to do a quick U sub. All right, that way I don't have to mess with the limits of integration here. All right, so I'll leave the top alone, x. The derivative of 1 over u is the natural log of the absolute value of u, which will be x squared plus 1. And then for the quick u substitution, we're going to divide by the derivative of the inside stuff, our u, which in this case is 2x. So the x's cancel. All right, and we get 1/2 times the natural log of x squared plus 1. Notice I've dropped the absolute value bars because x squared plus 1 is always positive, so we don't need the absolute value bars. Okay, now this, I could set up a limit, and I'm going to do that. This is going to be the limit as n goes to infinity of 1/2 times the natural log of x squared plus 1, and we're going to evaluate this from 1 to n. All right, and so we'll have the limit as n goes to infinity, and when we use the fundamental theorem of calculus, we'll get the 1/2 natural log of n squared plus 1 minus 1/2 natural log. When we plug in the 1, we'll just get the natural log of 2. All right, so as n goes to infinity, n squared plus 1 goes to infinity, natural log of infinity is infinity. This piece is going to infinity, then we're subtracting some finite number, so the whole thing goes to infinity. Okay, so this improper integral, right? The improper integral diverges. So by the integral test, A also diverges. Just for a second there, I couldn't remember what I called my series. Okay, so since this integral diverges, the series A also diverges. Hopefully now you see why I like to give these names, because they're much easier to write with just the name A than rewriting the sum all over again. All right, so let's look at another example. All right, let's consider this series here. This guy is definitely positive, because when k is 0, you still get 1/4, and as k increases, this will continue to be positive. The function itself will be continuous on the domain, and it should be decreasing as well, because as k increases, you're dividing by larger and larger numbers, and each step you have a smaller and smaller number, so it should be decreasing. So this series k going from 0 to infinity of 1 over k squared plus 4, it satisfies all the conditions of the integral test. Okay, so we can use the integral test. So let's do it. Okay. So what we're going to do is look at the integral from 0 to infinity of 1 over x squared plus 4 dx. Now, you could use k. It really doesn't matter what variable you're using. I just switch back over to x because that's what I'm comfortable with when it comes to integrals and functions. And then k's and n's is what I'm more comfortable with when we're dealing with sequences and series. Okay, it's just that's just like tradition. That's not necessarily right or wrong, but it's what I prefer to use. All right, so let's crank this integral out and see what we get. We are looking at a tan inverse pattern here, right? And thankfully, it's a perfect tan inverse pattern with a equal to 2. So we can integrate this directly as 1/2 times tan inverse of x over 2. And then we'll go from 0 to infinity. Okay, so as I mentioned before in the improper integral section, it's bad form to just plug infinities in. Right, infinity over 2, that's infinity. So this is tan inverse of infinity minus 1/2 tan inverse of 0. However, as long as you clean it up later, if you're ever going to show this to another math professor or something, you should be all right. Now, tan inverse of infinity, well, tan inverse looks like this. Okay, it has 2 horizontal asymptotes at pi over 2. So as x goes to infinity, tan inverse of x goes to pi over 2. Okay, so tan inverse of infinity, again, that's bad form, but this piece is going to pi over 2. Okay, so doing it this way can just save us some time. If you feel better about actually writing the limit out each time, go for it. But this will be 1/2 times pi over 2. So we'll have pi over 4. All right. So that means the improper integral converges. So this converges. So B also converges. Now here's a big caveat, okay? This does not mean the series converges to pi over 4, okay? The integral does. So we found that the integral, so it, that function might look something like this. We found that the integral converges. Okay. And so does the series, but remember the series is more representative of all these rectangles. So we see that while we get further out, they become pretty much the same. Around here, they differ by a lot. Okay? So the caveat is that this does not imply that the series k going from 0 to infinity of 1 over k squared plus 4 also converges to pi over 4. We don't know what it actually converges to, right? We'd have to do a little bit more work to kind of figure out how far off they are and when they start getting so close together that we don't need to keep checking the differences. It'd be a bit of work to actually see what, or approximate what this thing actually converges to. So keep that in mind. The integral test does not tell you what the series converges to, just whether or not this series converges. All right, for this next example, let's look at the series k going from 1 to infinity of e to the k all over 1 plus e to the 2k. All right, now this should, this will be positive because e to the stuff is always positive. Then it should also be decreasing because while the top and the bottom both go to infinity, the bottom, since it's e to the 2k, will be going to infinity a lot faster than the top will. Okay, so this should satisfy the integral test, so we can use the integral test. All right, so let's take a look at that integral. It'll be the integral from 1 to infinity of e to the x all over 1 plus e to the 2x. Now I'm going to use a quick U substitution because I want the denominator to be my u. Actually, no. No, I take that back. That's not what I want to do. What I want to do instead okay. I want my u. So this one, it might actually be worthwhile to do the U substitution. So I'm going to let u be e to the x. Okay, and that's going to make du be also e to the x. And the reason I want to do that is because when my first thought was I'm going to make the whole denominator u, but if I do that, the derivative of e to the 2x is 2e to the 2x, and I don't have an e to the 2x up here, but I do have an e to the x. So what I'm thinking instead is this is 1 plus e to the x squared in the denominator here, and that is a pattern that we're familiar with, right? That would be a 1 plus u squared. All right, so that should hopefully give us another, well, actually another tan inverse thing happening. All right, so yeah, we'll need to do an actual U substitution here. So my new integral I'll write in red. I'm not going to mess with the limits just yet. So this e to the x dx part, that is going to become du, and then we already know the denominator of the fraction is going to become 1 plus u squared. All right, so we'll get 1 over 1 plus u squared du. Okay, and now we need to mess with the limits. Okay, so here the limits, this is of course x equals 1, but this one here in the top is x goes to infinity. All right, so, and here's our u. So when x equals 1, okay, u is going to be e to the 1, which is just e. So our lower limit is just going to be e. Okay, our upper limit, well, instead of when x is equal to 1, it's as x goes to infinity, u, which is e to the x, well, e to the x also goes to infinity. Okay, so our upper limit is still infinity. This is still something to be careful with, all right? You never know. All right, and this is a tan inverse pattern with a equal to 1. Perfect. So we're going to get, this will be just tan inverse of u from e to infinity. Okay, so it will be the tan inverse of infinity minus tan inverse of e, and tan inverse of infinity, as we did in the last problem, that's pi over 2, minus tan inverse of e. I don't know what that is, but I do know that that's some finite number. Okay, so in other words, it's less than infinity. Okay, so the integral, the improper integral, converges. So by the integral test, our series C also converges. Okay, all right, so there we go. We were able to use the integral test here to show that this converged. All right, let's look at another example. All right, so let's look at this series. It's the series k goes from 2 to infinity of 1 over k times ln k all squared. Now, here's where what I was talking about before really comes into play. notice it doesn't really matter where our starting position is. Okay, in fact, we have to start it at 2 because we can't start it at 0 because that would give us division by 0, and we can't start it at 1 because that would also cause division by 0. And there's no real reason to reorder things and do a lot of work to try and make it so that we start at 1. All right, we'll just start at 2. This is positive because k is all positive here, and k is greater than 1, so our natural log will also be positive, and even if it wasn't, we're squaring it, so that's no problem there. It should also be decreasing, right, because we keep dividing by larger and larger numbers. All right. And then it should also be continuous because we're avoiding the problem spots. All right. So we can use the integral test. So let's take a look at this integral. Now, when we do this, of course, we need to match that lower limit. So, although, honestly, it probably wouldn't make that big of a difference, truth be told. But, you know, we can't go past, we can't go between 0 and 1 because we have, we would introduce another infinity. So it's just easier to do that. So we're going to look at the integral of 1 over x times the natural log of x all squared dx. All right, and here this is it's a 1 over u squared case, so we could think of this as a u to the negative 2. All right, so I'm going to do a quick u substitution. Okay, quick u substitution using the u to the negative 2, which when we integrate it will give us negative u to the negative 1, or negative 1 over u. All right, so I'm going to leave the 1 over x there. I'm going to have 1, and I should introduce a negative here, negative 1 over our u, which is ln of x. And then since it's quick u substitution, I didn't write that's what we were doing, but it's a quick u sub. With the quick u sub, remember, we always divide by the derivative of the stuff. Well, the derivative of the stuff here is 1 over x. And there we go. These 1 over x's cancel, which is exactly what they need to do if we want to use quick u substitution. And we're good to go. So now we're going to have negative 1 over the natural log of infinity, okay, minus, well, we already have a minus, so it'll be plus 1 over the natural log of 2. All right, so here's what happens here. ln of x goes to infinity as x goes to infinity. So this denominator is going to infinity, but we have a constant over that infinity, so this whole thing goes to 0. All right? So this whole thing goes to 1 over the natural log of 2. All right, so looks like this integral converges. So, by the integral test, our series, which I named D, converges. Okay, and there we go. There's how the integral test works. And yeah, I mean, basically if it's positive, decreasing, continuous, and fairly easy to integrate, of course, that's always subjective, right? What would be considered easy to integrate. You can apply the integral test. All right, so if we remember back to our improper integrals, we had this particular property here, that the improper integral from 1 to infinity of 1 over x to some power p, we discovered that it converges if that power is strictly greater than 1 and diverges if p is less than or equal to 1, right? Because of this, we get this automatically for series thanks to the integral test. So thanks to the integral test, okay, we get that this series, k going from 1 to infinity, of 1 over k to the p, well, it converges if p is strictly greater than 1, and it diverges if p is less than or equal to 1. All right, so that means if, like, I'm asked to look at the convergence of, say, this series here. Say I'm asked to find whether this series A converges, and it's the series 1 to infinity of, let's say, 1 over k to the 3. Well, I know that this converges. Right, this convergence is the power is equal to 3, which is greater than 1. Okay, and then I can also just right off the bat just say that if I have the series k going from 1 to infinity of 1 over the square root of k, well, I know that diverges. Because p here is equal to 1/2, which is less than 1. Okay? Series of this type are called p-series. Hopefully that is not too confusing to see why we call them p-series. Yeah, that's really what it comes down to. And we've already done the heavy lifting for p-series, thanks to improper integrals. However, what I want to show you for the last part of this section is how you can sort of manipulate how we think about the series in order to maybe simplify our work, or give ourselves ways to not have to, say, use the integral test, instead rewrite the series we have as a p-series. All right, so in this example, which I think might do a better job of trying to explain what I was trying to get at a moment ago, we have the series k going from 1 to infinity of 1 over k minus 1 all squared. Now, you might think that we would need to use the integral test here, okay? But it actually turns out, sorry, that shouldn't be from 1. Let's say 4. K is going from 4 to infinity. Okay, so what I'm going to do is, I don't want to say I'm reordering, but I'm going to renumber the series. Okay, because if I start looking at this series, so when I plug in 4, I'll get 1 over 4 minus 1, so that would be 3 squared. Then plus 1 over, now I'm going to put in the 5, so that would be 4 squared. Plus, and maybe I should put the k's up here, this would be k equals 4, k equals 5. For the k equals 6 step, we'll get 5. And so on. You'll see we have this pattern. And actually, it looks like we could, instead of writing it as k minus 1, we can instead write this series as, let's say it's the series n going from 3 to infinity of 1 over n squared. All right, these two series are the same. Notice I'm not rearranging the series, I'm just renumbering it. Okay, I'm just re-indexing it. I'm labeling it differently, but I'm not changing what makes the series a series. And that will, you know, there's some weirdness that comes up later that we have to be careful about. But this is a convergent p-series. So that means S converges. All right, now we could use the integral test here if we wanted to. If we just took the integral 4 to infinity of 1 over x minus 1 squared dx, well, the integral of this ends up being, if I do a quick U substitution, okay, it will be a negative 1 over x minus 1. Then I divide by the derivative of the inside, which is just 1. All right, so now we're going to get negative 1 over infinity minus 1 plus 1 over 4 minus 1. Okay, now this is 0. Like 1 over infinity just goes to 0. This is a 1/3. So this comes out to be 1/3. So this integral converges. All right. So yeah, we could do the integral test, right? That's nothing stopping us from doing that. But I don't know. I find this a little faster if you get practice with it. Okay, it can be helpful in certain situations. All right, for the next example or so, I want to show that we do have the tools to do quite a few things now. Let's say this is the series we have. It's a third plus a fifth plus a seventh, and you can kind of see it's basically odd denominators. Okay, so we need to try and turn this pattern into sort of a formula we can work with. So here's something that's going to be really useful. To iterate through the even integers, you would do 2k. Right? 2k goes 2, 4, 6, 8. Because when k is 1, you get 2. When k is 2, you get 4. When k is 3, you get 6. When k is 4, you get 8, etc. Okay, to iterate through the odd integers, there's two ways to go about it. It depends on where you're starting. But if you do 2k plus 1, and you start at k equals 1, right, well, when you put in 1, you get 1 times 2, so 2 plus 1, which is 3. Then when you put in k equals 2, you get 4 plus 1, which is 5. And then when you put in k equals 3, you get 7, etc. If you wanted to start at 1, for example, instead of 3, there are a couple things you could do. One, you could start at 0. So if you were to start at 0, you get 0 plus 1 is 1. Or you could look instead at 2k minus 1, which would start you at 1. Now the reason I'm telling you this is being able to do this is going to come in handy as we move forward. Also, if you've done any programming or you have to do programming in the future, knowing how to iterate through even numbers or odd numbers may be very important to you. Okay, so this is essentially how you do it, and you can actually do this with a lot of different numbers as well. Say you want to just iterate through the multiples of 3, well, you use 3k, okay, and so on and so forth. So it looks like that our pattern is this 2k plus 1. All right, so this is going to be the series k going from 1 to infinity of 1 over 2k plus 1. All right, well, this thing is always positive. Okay, it should be decreasing because the k is increasing, and each step of k we're dividing by a larger number, so this should be fine. All right, to use the integral test. All right, so we'll look at the integral from 1 to infinity of 1 over 2x plus 1 dx, which this is 1 over the stuff, right? So with a quick U substitution, this will be the natural log, the absolute value of 2x plus 1, all over the derivative of the stuff, which just happens to be 2. See how handy that quick U substitution stuff is? It's great. And I can pretty much tell that this is going to diverge because when we plug in the infinity here, the natural log of 2 times infinity, well, this is going to go to infinity. Plugging in the 1 doesn't do anything. That just makes this natural log of 3, but, this whole thing is going to infinity. Okay, so this tells me that that this integral diverges, so t diverges by the integral test. All right. All right, so for this example, we have the series, k going from 1 to infinity, of k over k plus 10 all raised to the k. All right. I'm very suspicious of this one. I'm pretty sure that this is not going to 0. Okay, because what's going on in here, this is going to 1. So the inside goes to 1. And then we're raising that to the infinity, right, as k goes to infinity. So this is a 1 to the infinity case. This is considered an indeterminate form, but I'm pretty sure, well, we need to check. We need to see if this actually goes to 0. So this is an indeterminate form. So let's just see. Let's let AK be the terms of our series. I'm going to take the natural log of both sides. And I'm going to kind of jump a step here just because we've done this a lot. All right. So what's going on here is as k goes to infinity, this piece goes to infinity, this goes to 1, so that means ln's going to 0. So this is infinity times 0. So that's still an indeterminate form. So I'm going to move that k thing down to get the natural log of k over k plus 10 all over 1 over k. And now we should have a 0 over 0. So we can use L'Hopital's rule. I'll give you a hint here. This will be a lot easier to differentiate if first we do this. Write it as ln k minus ln of k plus 10. All over 1 over k. Okay, that will just, because otherwise you're doing a quotient rule with this, and this will be a lot easier to differentiate. It's still a 0 over 0 case, all right? We just kind of changed the way it looked. All right, so when we do our L'Hopital's rule, we're going to get 1 over k minus 1 over k plus 10 all over, and the derivative of 1 over k is negative 1 over k squared. All right, so I'm going to simplify this top now, because now there's some stuff I can do. We can get this to be k plus 1 minus k all over k times k plus 1. And that'll be all over negative 1 over k squared. And the k's up top cancel. And I'm going to go ahead and invert and multiply. So I'll get 1 over k times k plus 1 times, this will be a negative. So I'll just go ahead and bring that negative all the way out and get a k squared over 1 when I invert and multiply. So notice that this and this cancel. And so this comes out to be negative k over k plus 1. So now we have matching powers of k here. So this goes to now negative 1. Oh boy. So that was a lot of work to get to here, but here's what we have. We have that the natural log of ak goes to negative 1. And when we introduce e, that's going to tell us that ak goes to e to the negative 1, or 1 over e, which the important part is that does not equal 0. Okay, so my ak's here, the terms of my series, they do not go to 0. Okay, in fact, they go to 1 over e. So v just diverges because of that, right? So v diverges by the divergence test, essentially. Now you might think that was a lot of work to show that, and it was. However, it's less work than trying to apply the integral test here, right? Imagine trying to integrate this guy here. Right? That'd be a real pain, right? But thankfully, we don't have to, because this thing doesn't satisfy the divergence test. All right, I think that's enough brain melting for one video, so I will leave it there. Hopefully that will get you rolling on the homework, and I'll talk at you all in the next one. Cheers.